Hello guys, welcome to the 2023 Waves paper for Level 2 NCEA. Let's get started. Question 1, the costume shop. Marco and Harvey head to the mall to buy props for the school show. Their first stop is the costume shop. The students start looking at hats in a concave mirror, so that's important. A concave mirror with a focal length of 25 centimeters. The mirror image is initially real. Okay, so define the term real as it is used in this context. Okay, so the first thing, they're basically asking, what do real images mean? And to put it into context, you could talk about the hat. So basically, I said a real image can be projected onto a screen. It is made with real images. It is made with real rays that converge in front of the mirror. So then I could also say something about a hat, like the image of the hats is made with real rays or something like that, just to put it more into this context as they asked. But it does look like an achieved question, so maybe that doesn't matter here. Alright, next question. Marco stands 40 centimeters in front of the mirror, so that there's your DO, although I don't think they're asking about that right now, but I'll write it down anyway. DO for calculations. So basically they want us to draw a diagram to show how the image forms, and they've already drawn us the image, they just want us to draw the rays to show how it works. So the first line is from the object straight to the mirror. This is meant to be a straight line, but I'm drawing on a laptop, so it's kind of hard. And then it goes straight through the focal point, so let's draw that ray. Oh, God, that went off. This is so hard to draw on a laptop. You guys get the point. I draw it with a ruler and it would go through the focal point, and then you draw your arrow to show that it's going this way, and it's going out this way, just to show that they're rays. And then the second line would be the one that goes straight through here, and then out this way at the same angle, and then eventually they'd converge somewhere around here, which is where the image is being formed. So if I was doing this with a ruler, then it would be completely straight, and then of course we need to draw the arrow to show where it's going, and out this way. So this is very messy, but I hope you guys get the point. Okay, so I already started doing the next question, but I'll explain. So it says to calculate the magnification. So first I'm starting by calculating DI, because we don't know how far the image is from the mirror. Then once we do that, we can use the equation DI over DO as M. So we know that the focal point is 25, it was given up here. And we know that DO was 40, so I've plugged those numbers in. And then we know that 1 over DI is equal to 1 over 25 minus 1 over 40. So if I do that on my calculator real quick, 1 over 25 minus 1 over 40, I get 3 over 200, which I don't have to write out as a decimal yet. So 1 over DI is equal to 3 over 200. And then we get that DI is equal to, why do I keep writing plus? Is equal to 1 divided by 3 over 200, which looks kind of messy right now, but that is 66.67 centimeters. Okay, so that there is the distance of the image behind the mirror. So that's where this image is. So this is 66.67 centimeters behind the mirror. Okay, so now we know this. Oh gosh, this went off. I'll try and move this back. So then now we need to calculate M. So we can now use, looking at the formula sheet, we can use di over do is equal to m. So m equals di, which is 66.67. We just calculated that. And that is over 40, which is our do. So if we do that on the calculator, we get 1.67. Actually, 1.67 centimeters. And the least amount of significant figures given in the question was 2, or 25 and 40. So we'd round that to 1.7 centimeters to 2 significant figures. Okay, so that there's probably a merit question right there. I'm guessing this might be either achieved or maybe merit. I'm not sure. Okay, this one looks like an excellence. Harvey now stands 10 centimeters in front of a concave mirror. By using a ray diagram and calculating the image distance and magnification, describe and explain the nature of the image formed. Okay, so first we need to draw our ray diagram, which will suck on this computer, but I'll try my best, guys. I'll try my best. Let me see if there's a ruler on here. No, there's no ruler on this app. Okay, so you're gonna draw a straight line. Well, that isn't too bad for a computer. And then you're gonna draw. So what is this? It's a concave mirror, but this time he's in front of the focal point. So you know that the focal point is 25, but Harvey's standing in front of the focal point. So we have the focal point. Actually, going back, I think I need to erase this because knowing how concave images are formed, we need more space for behind the mirror. Okay, so this is going to be our focal point, F. Okay, and then I'm going to have an object here. So object is Harvey, I guess. Then this is a concave mirror, so we're going to draw a concave mirror, and then we draw the lines out back, which I just can't do today, guys. Okay, there we go. So we want to draw a line that goes straight. Well, that's actually not too bad. Okay, we want to draw our focal point around the same the exact same distance on this side. I just don't have the capacity to do that right now. And then it goes through the. Oh, right, sorry. So then we have it appear like we drew this line, and then the ray would appear to come from this focal point out. Yeah. So that's how it works. So that okay. This would actually be a dotted line out here because it's the virtual side. And then we have the second one, which is to the middle of the mirror and out in the same angle on the other side. Then we just draw it out with a dotted line, and eventually they meet. And hopefully you can see that our image is bigger than our object. So that's I. And really I should draw O for the object here. Okay, so that's basically how you do it, but you draw it with a ruler. And I actually haven't done too badly. Okay, so now they want us to calculate the DI and the magnification. Okay, and then describe the nature of the image. Okay, cool. So, DI. So again, we're going to use the same 1 over F equals 1 over DI plus 1 over DO. And then we're going to do 1 over 25. That's our focal point. 1 over 25 equals. Now this time he's standing 10 centimeters. So that's our DO. 1 over DI plus 1 over 10. And then, so 1 over DI is equal to, what was it? 1 over 25 minus 1 over 10. So if I quickly do that on my calculator, over 25 minus 1 over 10, it's negative 3 over 50. So let me just write that down quick. Negative 3 over 50. And then we can do di. Di is equal to 1 divided by negative 3 over 50, which is negative 16.7. So the reason we get a negative answer is because it's a virtual image, so you might write down it's a virtual image, hence negative. Okay, so now you've given a reason for why it's a negative answer. And then you can move on because they want us to calculate the magnification as well. So let's do that quickly. So m equals di over do. So that is, what was it, 16.67. This time we don't use the negative. We ignore the negative to calculate the magnification. Over do. What's do? That's 10. So that is, surprisingly, or maybe not so surprisingly, equal to the same as our last magnification, which is 1.67. And magnification has no units. So m equals 1.7, and that is to 2SF. Just gonna make sure I didn't put any units the last time I calculated magnification. Oh yeah, I did. Okay, no, magnification is not in centimeters, it's just, it hasn't got any units. Okay, and they also wanted us to do the image, nature of the image. So, nature of the image is upright, virtual, and enlarged. And they also wanted us to explain, which I'm not really sure what that means. They said describe and explain. Usually that means they want us to do a little bit more than just say what type of image, but I'm not actually completely sure, so I'm just gonna move on. They might want us to explain that it's like 1.7 times the amount, which would make sense. So you might need to say the image is 1.7 times the object. Is enlarged. So they might want you to say something like that. I'm not actually sure, but that's all I can think of. So let's move on to question 2, the wishing pond. Okay, the students walk past a wishing pond for a local charity. People throw coins into the water, and these are collected at the end of the day. So as the students sit on the side of the pond, they notice coins appear closer to the surface of the water than they actually are. Name the physics phenomenon that causes the coins to appear closer to the surface than they are. So that is refraction. And if you don't know if you don't know how to figure that out, you can actually just move on, and you can see that this here is refraction, so the question is basically giving you the answer. And it just says name it, and I think this is just an adhesive question, so that's all you need to say. The following ray diagram shows the ray as it enters and leaves the water. The refractive index of water is 1.33 and air is 1.00. Calculate the angle O shown at the surface of the water. Okay, so you have to be careful here, because I think that this is the normal, right? This line here. So actually, they want us to calculate this angle. So okay, I'll just show you as we do it. Okay, so we use this formula n1 sine theta. I don't really know how to do theta. I'm just gonna do an O for a 0 for theta. 1 is equal to n2 sine theta 2. Okay, that's Okay, so let's do it on a new line. Okay, so our first thing is water, so we're going to do 1.33, which is N1, times sine theta 1, which we don't actually know yet, so theta 1 is equal to N2, which is 1, times sine, what is it, 40? Yeah, 40. Okay, so 1 times sine 40. Cool. So then what you want to do is you want to do sine 40 over 1.33. So let me just do that. Sine theta 1 is equal to sine 40 over 1.33, which, if I quickly do that on my calculator, 1.33. Oh, hang on. I think I need to do this properly. Okay, so we get 0.48 or something. 0.48. So then we have sine inverse. Sine inverse of 0.48 to get this angle here, which, let me just actually draw this out. So what we're actually calculating for is this angle. That's why I am right? That's the angle that will calculate. I guess when we calculate it, we'll see, because if it's a big number, then maybe not. Okay, wait. Shift sine inverse. Okay, so we get, is equal to, wait, no, let me just continue typing here. Is equal to 28.9 degrees. How do I do the degrees on here? I don't actually know. Okay, just pretend that I did a degrees symbol, because I don't know fully how to do it. And then, so that there. Oh, actually, I don't think you need to minus anything. I think that's it, because if they wanted you to calculate, like, if this was 28.9, that's way too big. So I think 28.9 is just this angle here. Okay, so that's it. That's the degree. That's the angle. And then you'd round it to 3 significant figures, because that's, yeah, 3 significant figures. So that there's 3 significant figures. So let me just do that. 3 SF. So you'd know, like, this looks like 28.9 degrees, because if you were to do 90 minus that, then that's too much. Like, they don't want us to calculate. So let me just get rid of that. That's a mistake, guys. Okay, let's move on now. Okay, so next we have a diamond, and it's caused by total internal reflection. So let me underline that, because that's kind of the next part they want us to know. Okay, so we have the refractive index, we have the critical angle, and we also have the speed of light in air. A ray of light passes through the boundary between air and the diamond. Okay, so I think that's the light that they're talking about. So you can see that it's been you can see that it's been totally internally reflected, because the light is going out like that. So calculate the speed of light in the diamond. Okay. So we use a handy equation for this. We use N1 over N2 equals V2 over V1. Okay, so let's do this now. So N1 over N2. So we've been given that the refractive index of air is 1, so we can use that. So N1 is 1 over N2, which is 2.42. We've been given that. 2.42 is equal to V2 over V1. So V2 is the speed that we want to calculate over V1. So V1 is going to be the speed of light in air, which is 3 times 10 to the power of 8. Let's write that down. 10 to the power of 8. I'm not sure. There we go. 8. Okay. Okay, so that means we can do V2 equals 1 over 2.42 times 1 over 2.42 times 3 times 10 to the power of 8. This is just rearranging simple algebra. So if I do that on my calculator real quick, 1 over 2.42 times 3 times 10 to the power of 8, we get a large number. Let me write that down. So we get 1, 2, 3, 9, 6, 6, 9, 4, 2, 1. 9.242.1. Okay, so remember how they want us to round it to 3 significant figures? So we have to do that. And the best way to do that is to actually just write it in standard form. So that is equal to 1.24 x 10 to the power of 8. Okay, I hope you guys know about standard form because I can't be bothered to explain it right now. But I guess you also could write 124 followed by 8 zeros, which would also be fine. And then just make sure that you write meters per second, which is the unit. Meters per second, and then to 3 SF. Okay, let's move on to the next section. State what happens to the frequency of light. Okay, so this is a normal thing. The frequency never changes. So the frequency doesn't change. It remains constant. Okay. Let's move on to the next question. Using appropriate calculation so that the critical angle for diamond is 24.4 degrees. Okay, let's do that. So I think this also looks like a merit question. Okay, so we want to prove that the critical angle is this, right? We've been given it, but they want us to prove it. And to do that, we have to use the refractive index of diamond and the refractive index of air. And remember how the critical angle can only happen if it's going from a more dense to a less dense medium. So this is the incident angle, this is the refractive angle. Okay, so this is our thing here. So we use Snell's law, n1 sine theta 1 is equal to n2 sine theta 2. Okay, so let's just fill this out. So we're given that the refractive index is 2.42. Let's do that. 2.42. And we want to prove the refractive angle, so we don't know it yet, so that's why it's theta 1 is equal to 1 times sine 90, because for the critical angle, the angle of refraction is always 90. So then if you know your maths, you know that sine 90 is equal to 1. So then you can just go ahead and say sine inverse of 1 over 2.42 is equal to, let me just do it on my calculator real quick. Shift sine inverse of 2.42. And that is equal to 24.4. 0.4 degrees, just pretend I put a degrees and then 3 SF. And then, yeah, so you basically proved what they're asking you to prove. And that's pretty much all you need to do. Explain total internal reflection in terms of the conditions required and include a definition of the critical angle. Okay, so I'm just gonna, for total internal reflection, I'm just gonna write TIR for brevity and fast typing. So, for TIR to occur, the angle of incidence must be greater than the critical angle. The light ray must be going from a more to less dense medium, like diamond to air. Okay, and then you also want to put something about the critical angle, because they want us to talk about what the critical angle means. So let me just make that other. Let me just put another text box here. Okay, so what is the critical angle? The critical angle is the angle of incidence for which the angle of refraction is exactly 90 degrees. Just pretend I put a degree symbol there, because again I don't know how to. And the ray is reflected along the boundary. It is neither reflection nor refraction. Okay, so that's pretty much all you need to say, I think. I don't think there's anything else, so let's move on to the final question. Question 3. So, there's 2 different types of glasses, thick and thin. Of course I can't see the image, but that doesn't really matter. So how does the focal length of the thin lens compare to the focal length of the thick lens? Okay, so in the thick lens, the rays bend more, and that's because it has a higher refractive index for a thick lens, because think about it, there's more glass, so there's going to be a denser medium, so the rays are going to bend more. It's like more refraction. And so if you think about it, if I just draw a quick diagram, then if you think about how it refracts, so let's assume that this is our lens, and we have our ray. Assume that this is a thick lens, right? It's gonna bend a lot, right? So that means that our focal point, if it touches the focal point here, it's gonna be less, right? Because it's bending a lot. Versus if we had a thinner lens, then it would go further like that. Okay, so I'm just gonna erase this now. I think you guys get the point. Okay, let's go back to the thing. So in a thick lens, the rays bend more, meaning that they have a shorter focal point. In a thin lens, the rays bend less, meaning that they have a longer focal point. Yeah, there we go. Focal length, actually. Length. Alright, that's it. That's pretty much all you have to say. I think this is an achieved question. Let's just put that there. Okay, so let's keep going. A different set of glasses has convex lenses with focal length of 30 centimeters. Complete the ray diagram. Okay. So again, I always like to draw this ray first, which just goes straight through the middle of the lens and out. Just makes it easier for me. Okay, so this thing is in front of the focal point, so we know we're gonna get an enlarged virtual image. So let's just, why can't I draw here? Oh, there we go. Okay, so we're gonna have dotted line coming out, and then we're also gonna have a ray that goes like this, and it comes out like that through the focal point there. Sorry. And then if we extend the ray backwards. Oh, why isn't it writing? Okay, sorry guys, this is meant to be a dotted line, but I just couldn't draw. Wait, let me try that again. Okay. No, not text. Draw. Okay, so like that. Okay, so basically it's like that, and then we have our image where the rays converge, or somewhere here. So you can see that it's enlarged, and I'm trying to make my line straight here, but I'm getting tired, so let's just move on. Okay, so it's an enlarged upright virtual image. The students walk further along, and so basically, I'm not going to read the whole thing out, but basically there's a speaker here, and it's producing a low-pitched guitar bass noise, and then a high-pitched electric guitar noise, and the question is asking, why can the student hear only bass here, but then high pitch and bass here? So, why is that? Okay, so and they also say that you can use the diagram above, so I'm just gonna do that real quick. So if we draw a rays, so the high pitch has lower frequency, which means it has shorter wavelength. So we have like shorter wavelengths. Okay, just pretend that these are all equidistant apart. I can't be bothered to draw this, okay? So this is at low frequency, and these are meant to be curved lines. I just can't do this right now. Okay, and then they eventually get to the students' ears, but then they can't really go any further, so they stop there. Versus, let's see if I can get a different color on. Okay, versus we have our bass guitar, which is going to have longer wavelengths, and it can diffract more around. Okay, and again, this is meant to be the same length apart. Okay, so then you can hear this here. Alright, so let's move on. Let's just get the text. Okay. So, why do they hear the bass here but not, but why can't they hear the high pitch? So let's just write a quick answer to that. So we have the electric guitar, just ignore any spelling mistakes right now, has a high pitch noise, so it has a high frequency. This means it has a low short wavelength. Since short wavelengths diffract less, they can't be heard by the student because the sound can't diffract around the more to the student's ears. Oh gosh, what happened? Did I accidentally? Oh, there we go. Sorry guys, students' ears. Okay. And then I can't be bothered, but basically you'd write the exact same thing, but it would be an opposite. So you'd write that the bass guitar has a low pitch noise, so it has a low frequency, and this means it has a long wavelength, and since long wavelengths diffract more, they can be heard by the student, because the sound can diffract around them all to the student's ears. And then I'd also put in a V equals F lambda, which is the, let me just put that in real quick, which is the, I don't know how to put in lambda, I'll just write it in. Okay, so I'd also put in that formula, which I can't draw lambda on this keyboard, but you guys get the point, and then I just explain the equation. Okay, let's move on. Later they pass by a hall where the band is playing instruments. So basically what's happening is that the rays are coming out from these two holes, and it's asking us to draw a diagram of how they come out, but I really can't be bothered to draw my own, so I'm just going to use this one here. So basically the waves are going to come out like this. Oh my gosh, that is terrible. Let me redraw that. Like this. And they're all going to be the same length apart, okay? I just can't do this. Okay, so that's probably enough. And then you have the same exact waves coming out from the other side because they're at the same frequency and same noise and same waves, whatever, okay? And then you're going to get something called nodal and antinodal lines, so wherever a crest and crest meet, so if I pretend that this first line is a crest. And this is a trough, and then this here is crest, trough, trough. So this point here is an antinode, or antinodal line, right? Because two troughs are meeting. Yeah, and I just draw the lines out, but right now I'm not gonna do it, but I hope you guys get it. You're all physics students, you know what I'm doing. And then, what are they asking here? They said, identify, describe, and explain the physics phenomena. Okay, so this is basically all about constructive and destructive interference. So let me just write a quick answer. So when two identical waves superimpose, they produce an interference pattern. So right there I've named the phenomenon, which is interference. At points where two crests or two troughs meet, constructive interference occurs. The amplitudes are added. These points are called antinodes, and maximum sound can be heard. The path difference is whole, so n equals 1, 2, 3, etc. And that's pretty much all you have to say about the constructive interference part. Then let me talk about destructive interference. Okay. At points where a crest and trough meet, a destructive interference occurs. The amplitudes get cancelled. Get subtracted, actually. Subtracted. The waves get cancelled. And, yeah, okay. So, these points are called what? Nodes. And minimal sound is heard. Then the path difference is n plus half. Okay, and then I think that's all you guys need to say, really. Because what did it ask you to do? It said to use physics concept to identify, describe, and explain the phenomena. Yeah, I mean, we did that. Yeah, I think that's basically it. And that's all you needed to say, and that is the 2023 paper done. Thank you guys for watching so much. I'm so happy that, I hope you guys learned something, actually. And I hope this video helped. Thank you very much.